Good morning, everybody. Welcome to Kinematics. Today we're going to talk about position, displacement, and distance. This falls under the chapter of kinematics. All right, so displacement, position. Let's start with position. Position is the location of an object. It has the symbol of X. So we'll think about this as a location. And the symbol is the letter X. It's the letter X if we're talking about just left and right, movement left and right. If we're talking about movement up and down, that would be Y. The symbol Y would be position as well. Or if we're talking about movement towards the camera, away from the camera, that would be the Z direction. So we can have movement in any direction, and it would be a combination of X, Y, and Z for your location. We're going to start out with one-dimensional, that's a line, and then we're going to talk about some two-dimensional motion in a future video. So the symbol for position is X. Position, it does matter what the direction is. We define a point where the position is 0. So where is X equal to 0? We can choose that, and then after we choose where X is 0, anything to the right of that would be a positive X, and anything to the left of that would be a negative X. So in this simulation, the position is currently at positive 80 meters because we've defined this point right here to be 0 meters. Okay. So let's go over to 80 meters where our object is. So this object's position right now is 80 meters. All right. So position is a location. It can be X, it can be Y, it can be Z. How do we measure position? We use the SI units, so it would be meters. So the unit would be the meter. So this M is not the same thing as like a symbol M. This M would be, like for example, X equals 80 meters. So this X is a symbol. So we could think about this letter X would represent the position. So we're just saying position, and then the equal sign is the word is, and then the quantity itself is 80 meters. Okay, so 80 meters, a number and a unit together make up a quantity. So there's a number and there's a unit. A number and a unit. Together they make up a quantity. QTY for quantity. This is what we would call a variable. Now, because the direction does matter for position, we would say that position is a vector quantity. A vector quantity means the direction matters. So what we do then is what does that mean? That means whenever we write this letter X, we could write a little arrow over top of it to show that the direction does matter. So in kinematics, position is a vector quantity. It gets an arrow over top of it. Displacement is a vector quantity. And distance is not a vector quantity. So I'll take that away. Okay, so that was position. Next we'll talk about how positions can change. So we're going to make this x at, I don't know what time it is. I don't have a timestamp on the screen. It doesn't tell me what time it currently is. So I won't worry about that right now. We'll just call this the first position. So let's say x1 equals 80 meters. And we'll put a little symbol. And now we have to put a direction. So we're going to say to the right of the origin. So I'm going to put that in parentheses so I don't have to write it over and over again. All of these are going to be positive, so positive numbers for this example, because this box is never going to go to the left of the origin or it would fall off the ruler. Okay, so that is position. Done. Now we need to talk about the next thing, which is displacement. All right, displacement is a change in position. Change in position. The symbol is delta x. Delta x. This symbol is called delta. Looks like a triangle. It's called delta. What does delta mean? It means change. So if we have delta x, that means a change in the variable x. And that means something for math as well. So we can write an equation for it. Based on this definition, the equation for a displacement would be delta x, a vector quantity, is a later position minus an earlier position. So let's call this x, a later position, minus an earlier position. And for this I can put a little x0. So this just means initial or earlier. That little 0 means initial or earlier. So x later minus x earlier. It's a difference. The difference between the two positions would be the displacement. And this would give us the straight line distance between the two. So let's change the position. We had an early position, so x0, of 80 meters. So that was a vector quantity, and I'm going to put a little plus to show that it's to the right of the origin. That'll be a little shortcut for us. Now let's change the position, and we'll note a new position. Let's go this way. Whoops, I have to hit play. All right. Let's go over this way, and then we're going to come back over this way, and then we're going to go this way, and then we're going to go this way. We're going right and left, and let's see where we end up. Okay, that works. Let's hit pause again. So now I've changed the position by moving to the right and to the left, and to the right and to the left, and to the right and to the left, and everything that happened in between, I don't know. I don't know what happened in between. There was a lot of stuff that happened in between. I'd have to, did I record? Can I record? I can't record. All right. A lot of stuff happened in between. But I do have a final position. The final position is positive. Okay, 66 is this long line. 66.1, 2, 3. And the position is given by the center of mass, which is right in the very middle of this box where this black line is. And that seems to come about like 80% of the way from this tick mark to this other tick mark. So I would say 0.1, 2, 3. So 66.3, and like 8/10 of the way to 0.4. So I can write 66.34. No, 38. There we go. Because that little 8 was the 80% of the way. Measured in meters. And now I have two positions. So I could say, okay, well, what was the change in the position? Well, the change in position is a later position minus an earlier position. The later position was 66.38 meters. Now, why am I doing that? 66.38 meters. And I always write the letter in my calculation for the meter, for the unit. I include the entire quantity. I don't just write the number. Minus 80 meters. And technically this 80 meters is precise down to the hundredths place. So I would say 80.00 meters is what it actually is. So I'm actually going to do that. Let's move this. Let's get it out of here. And we'll put 80.00 meters. Okay. And now I just have to do a calculation. 66.38 minus 80. I got negative 13.62. Is the camera showing that? There's my calculation. Negative 13.62 meters. Okay, so I had a quantity in meters minus a quantity in meters, and when you subtract units, they just became the same unit. So, 20 apples minus 3 apples would be 17 apples. When you take apples and subtract apples, you get apples. When you subtract meters from meters, you get meters. Or if you add meters to meters, you get meters. Okay, so the unit doesn't change when you're adding and subtracting. So, great. What does this negative mean? It means a direction. So the better way to write this would be to say the magnitude, which means the absolute value of the number, 13.62 meters, and then I would include the direction instead of the negative sign to the left. Because in this situation, positive and negative are right and left. Positive is to the right, negative is to the left. That's the way it was defined within this situation. You have to read the situation and then use the directional system that they have. All right, so that's it for displacement. Notice displacement doesn't tell me what happened in between. Doesn't tell me what happened in between. Well, let's go back to having the box at 80 meters. And let's talk about distance. Distance is how far you've gone along a path. A more formal definition can be found on the internet or in a textbook. There are lots of different symbols that can be used for distance. S is one of the symbols. Don't ask me why. But we're going to use the symbol D. Oh, let me note that for delta x, that was a vector quantity. Now D, distance is not a vector quantity. So the direction of travel is not accounted. Direction not considered. So we would say this is a scalar quantity. So the way we calculate a d, a total distance traveled, equals a bunch of smaller distances traveled. So d1 plus d2 plus d3 plus ... Sometimes distance and displacement are the same. Let's do an example. Example 1. Let's say x1, let's say x0 equals 80 meters to the right of the origin. All right, that'll be the first position. I'm doing positions right now. This is a position. And let's define a second position. So let's move this thing. And we're going to pay attention. I'm going to move it to the left, and then I'm going to move it to the right. So I'm just going to use my arrow keys to move this thing to the left for a distance, and then I'm going to let go and let it stop. Okay. I'm going to pause it now. So the second position that we note that it got as far to the left as positive 76, and how far? 76 is right here, this long line, and then short line 0.1, 0.2, 0.3, 0.4, 0.5, and it looks like it stopped dead on 0.5. So we'll say 0.50 meters. And this is another position. So we'll call this position 0, and this is position number 1. So we'll say x1. And then let's define another position. Oh, sorry. Before we do that, let's figure out what the distance was between these two. So between these two positions, what was the distance traveled? Well, that would be how far is it from 80 meters to 76.5 meters. So I would say I would be subtracting there. So that's how far we would get, the difference between the two. So 76.5 minus 80, or I could do it the other way around. See, the negative is not going to matter because this is a scalar quantity. The direction is not considered. So even though I got math of negative 3.5, even though I got negative 3.5, I'm just going to be writing 3.5 meters as d1, the distance traveled first. But when I write delta x1, that's a vector quantity, the direction is considered, so that would be minus 3.5. I guess I should have zeros at the ends of these. Negative 3.50 meters. So the distance was not negative, the displacement was negative. Okay. So let's keep going with this example, and let's define a third position. We'll call it x2 because we had x0 and x1. So now I'm going to start the simulation, and I'm going to move the box to the right a little bit. Okay, I moved it to the right a little bit. So the new position is now 78. I see 78 right here is the long. It hasn't gotten all the way to 79 yet. 78.1, 78.2, and I'm just barely shy of 78.3. So 29, I guess I'll say. Unless I think I'm halfway. No, that's fine. So this will be called position 2. Okay. So let's talk about from position 1 to position 2. Call that D2. So I went from 76.5 to 78.29. So let's do that calculation. The difference between those two is 78.29 minus 76.5. Okay, and for that, I got 1.79. Do I need to put a little plus on this? No, I don't, because distance does not consider the direction. But delta x, so delta x2, the difference, I could say delta x1 to 2, or I could just say 2, that's fine. That's the naming convention that I came up with for now. So I got plus 1.79 meters. Okay, so let's calculate from 0 to 1. I got a distance of 3.5 meters, and from position 1 to position 2, a distance of 1.79 meters. So what would the total D be equal to? The total distance from 0 to 2, from the point in time times 0 to the point in time 2. So I take 1.79. So these would be adding up. Let's say 3.50 meters of distance plus 1.79 meters of distance. So the total distance I traveled, 3.5 plus 1.79, is 5.29. Okay. The displacement, consider this the direction. So the displacement over this entire from time 0 to time 2 would be negative 3.50 meters plus positive 1.79 meters. So I could be adding up the positive and negative displacements. That's like one method of doing it, but I'm going to show you another way that works as well. So negative 3.5 plus 1.79 is negative 1.71 meters. But the other way to do that, I could also be calculating it this other way. I could say final position, x final, like a later position, minus an earlier position, so I'll say I for initial, right? That's what we defined earlier as the equation for displacement. So one way so it's change in position. That's a difference in position. So let's calculate it this way, this other way. The final position was positive 78.29 meters. That was x2, position 2. And position 0 was positive 80.00 meters. So I'll do 78.29 minus 80, and I get negative 1.71 meters. So it's the same. I got the same displacement using the two different methods, and it's negative 1.71. And in this example, I have different. They're not equal to each other. They're not the same. So distance isn't necessarily the same thing as displacement. Sometimes distance is the same thing as displacement when an object is just going in one direction. There's no direction change. I hope this was helpful. There are some Khan Academy assignments that you guys could do now based on what we've just learned. And I hope this was helpful. Have a good day. Email me with any questions.